Yes. Good morning, students. Am I audible? Hello.
Yes, sir.
Good
Yes,
morning,
sir.
sir.
Yes, sir.
Good morning. Good morning.
Good morning, sir.
So, am I audible? It's okay.
Yes, sir.
Yes, sir.
Okay. So now I'm sharing the screen. Whiteboard is visible. Hello.
Sir. Yes, sir.
Hello.
Yes, sir.
Yes, sir.
Yeah. Okay. So now today we will see the mathematical modeling of. Yes, we start now.
सर
हाँ.
हॅलो सर
Hello.
सर तुम्ही ते हॅलो
हाँ हाँ बोल.
हॅलो हा सर ते रेकॉर्डिंग तुम्ही लेक्चरचे सर कुठे पाठवतात?
नाही नाही ते सेव्ह करतो माझ्याकडं. मी आजपासून चालू केलंय.
अच्छा ओके सर.
हा.
तर ते तुम्ही नंतर ग्रुपमध्ये टाकणार आहे?
हो पाहिजे असेल तर टाकेल तुम्हाला काही हरकत नाही.
हो सर पाठवून द्या एकदा परत म्हणजे
चालेल
बघायला नंतर.
चालेल चालेल ठीक आहे. Mathematical modeling of physical system. I just want to brief you about mathematical modeling of physical system. Now, in this one, we will see the one of the example. Execute a project within the boundaries of scope and let us say this is current. So, quickly you understood most of the part of the project management manual. Let's say it is I of t. How to manage the triple constraint? Write down next topic. How to manage the triple constraint? This is R. The triple constraint appears simple, but that's only on the surface. Each of the 3 points of this triangle can be unpacked to reveal a deeper meaning of it. This is R, L, and C. If you want to manage cost, the financial commitment of the project is dependent on several variables. And let us say currents flowing. This is IR. Currents flowing through the inductance is IL. And currents flowing through this is, let's say it is IC. There are some variable cost for any project. Right? Variable cost is right. Labor, which must be calculated. So, differential equation of given circuit. We have to write down the differential equations of a given circuit. Now see here, in this one, the resistance, inductance and capacitance, they are connected in parallel. Okay, they are connected in parallel, and they are connected across a current source. They are connected across current source I of t. So the total currents flowing through the circuit is I of t, and this I of t is divided into three parts. One is IR, one is IL, and another is IC. Another is IC. So the total applied current, that is I of t, Jagdish, I of t, it is the current, total currents, which is divided into three parts. One is IR, second is IL, and third is IC. Okay. Now we have to find out, or we have to write down the differential equations of a given circuits. Now see here, in this one, here we will assume there is a node and whose voltage is V. Whose voltage is V. Now see here, this is our node 1. This is our node 1, and this is our reference node. This is our reference node VRF. It is equals to 0 volts. It is equals to 0 volts. We assume that this is the reference. This is the reference because uh, here we assume this one because R, L, C are connected together, and the negative part of I of t is also connected to this point. That is the reference node point. So we consider this is a reference node and assume that the reference node voltage is 0 volt. And this one is the node number 1 whose voltage is V. Whose voltage is V. Now see here, the resistance R is connected between the V and the reference node. So that means the voltage across the R is V. Similarly, the inductance, it is connected between the node V and the node reference. So the voltage across the L is again V, and C is also connected between the V and the reference node. So the voltage across the C is also V. Now see here, R, L and C, they are connected in parallel. So definitely they have a same voltages across each components. Resistance, inductance and capacitance are connected in parallel. So they carry the different currents, but the voltages are same across all the components. Across all the components. So here, here, apply here in the solution, apply KCL to the node. KCL to the node. Now see here, in this node at the V, I of t is coming, is a incoming current to the node. IR, IL and IC are the outgoing currents to the node. So we can write down I of t, I of t it is equals to I of R plus I of L plus I of C plus I of C. The currents flowing through the resistance, currents flowing through the inductance plus currents flowing through the capacitance, it is equals to total currents, that is I of t. That is I of t. So this we can write down I of t, it is equals to I of t, it is equals to currents flowing through the resistance IR. What is the voltage across the resistance R? That is V. So we can write down it is V of t divided by R plus what is the voltage across the inductance? That is V, and the current's inductance value is L. Inductance value is L. So we can write down the 1 by L integration of V of t into dt plus voltage across the capacitance is against V and the capacitance value is C. So we can write down it is C into dVt by dt. So this is our current equation. So this is our current equation. Let us say this equation is A. Let us say this equation is A. Now take Laplace transform of the equation of the above equation. I of t becomes I of s. It is equals to 1 by r is constant. So we will take 1 by r as constant and v of t becomes v of s plus. This is 1 by l is constant. So 1 by l we have to take it outside. And integration is 1 by s. 1 by s. So we will write down here s into l into v of s plus C as it is and d by dt is s. So s into c and v of t becomes v of s and v of s. So we can write down I of s, it is equals to 1 by r plus 1 by s into l plus s into c multiplied by v of s multiplied by v of s. So this is our equation. So this is our equation, or we can write down I of s, it is equals to, we will take s l r common. So here is s into l plus r plus S square RLC multiplied by V of S. We will take the LCM of these ones, R and SL. So S into L into R. So that is our this one. So I of S, it is equals to S square RLC plus S into L plus R divided by S square L into R into V of S. This is our um, equation. This is our equation. Now suppose if you want to find out a transfer function that is here in the circuits. Current is the input and the voltage across the components are the output. So we will take output, that is V of S divided by I of S. It is equals to V of S divided by R of S. It is equals to S into LR divided by S square RLC plus S into L plus R plus R. This is our transfer function. This is our transfer function. If you wants to find out the transfer function, and equation A is our differential equation. Equation A is differential equation. Differential equation. We have to write down what is our statement. Write the differential equations of the given circuit. Write the differential equations of the given circuit. So I of t, it is equals to V of t divided by R plus 1 by L integration of V of t into dt plus C into dvt by dt. Now see here, or this we can simplify like this one. Suppose if you want to write down it into the uh, derivative forms, then we can have like this. Okay. Uh, Equation A. One minute. Equation A. We will write down the equation A once again. Equation A becomes I of t, it is equals to V of t divided by R plus 1 by L integration of V of t into dt. We will write down as it is integration of V of t into dt plus C into dvt by dt. So this is our equation A. This is our equation A. V of t, this V of t, that is the voltage. V of t, it is equals to d phi t by dt, rate of change of flux, that is nothing but the voltage. Rate of change of flux, that is nothing but the voltage. So V of t, it is equals to d phi by t, d phi t by dt. So we can write down I of t, it is equals to 1 by R is constant, so we will take it outside, and this becomes d phi t by dt plus this is V of t divided by R. We can write down 1 by R is constant and V of t is nothing but a d phi t by dt plus 1 by L is constant and integration V of t is what? D phi t by dt into dt plus C plus 1 minute. Plus C. This is V of t. V of t, it is equals to d phi t by dt. So this becomes d square phi of t divided by dt. We will replace V of t by d phi t by dt because voltage is nothing but the rate of change of flux. Rate of change of flux. So I of r, I of t, it is equals to 1 by r. This becomes d phi t by dt plus 1 by L. Now see here, this is integration of d phi t by dt into dt. So this becomes phi. This becomes phi of t plus this becomes d c into d square phi t by dt. Phi t by dt. So this is our here is the square, here is the square. Okay, because it is d square by dt square. So I of t, so I of t we can write down, it is equals to c uh, c d square phi t by dt square plus 1 by r 1 by r d phi t by dt plus phi t by L. Phi t by L. So this is our differential equation. So this is our differential equation. This is equation B. This is equation B, and equation B is a differential equation. It is a differential equation. C into d square phi t by dt square plus 1 by r into d phi t by dt plus phi t by L. That is nothing but our differential equation. That is nothing but our differential equation. So this is the solution for this given example. This is the solution of this given network. Hello. Hello.
Yes, sir.
Yes, sir.
Yes, sir.
Yes. So you have to remember the differential equation because in the differential equations is important to find out the analogy, force to voltage and force to current analogy. Force to voltage and force to current analogy. Now see here in the next page we will see the, let us say this is module 2, modules 2, and we will find out F2V and F2I analogy. F2V and F2I analogy. F2V means what? Force to voltage. F2V means force to voltage analogy. And F2I and F2I means force to current analogy. Force to current analogy. We have to find out force to voltage and force to current analogy. That means we can directly convert mechanical circuits into electrical circuits in the form of voltage or in the form of current, in the form of input as a voltage or in the form of current as a input. So this is F2V and F2I analogy. F2V and F2I analogy. Now see here for this one in the last period that we have seen, consider mechanical circuit. Consider mechanical circuits. Now see here, let us assume that these circuits that we have studied in the last period, this is K and this is F. This is M. Let's say this is F of T. Okay. And here we have the displacement X of T. X of T. Okay. So here M is mass, F friction, K damper or the spring, F of T applied force, and X of T is a displacement. X of T is the displacement, and dxt by dt, dxt by dt, that is your speed. Dxt by dt, that is nothing but the speed. Okay. 1 minute. Dxt by dt, this is the speed. Now see here, these are the components description. In this given mechanical circuit, M is mass, F is friction, this. Then small f. There are the two F are there. One is F of T and one is small f. F is the friction or the damper. Friction or the damper. Or damper. K is the spring. Okay, F of T is the applied force and X of T is the displacement. When we apply the force to the any system, we get the displacement, which is denoted by X of T, and if we take the derivative of the displacement, then we get the speed. Dxt by dt, it is nothing but the speed of the system. Speed of the system. Now see here, from this equation, from this one, yesterday in the last period that we have derived the equation f of t, it is equals to m d square, m d square x of t divided by dt square plus f into dxt by dt plus k into x of t, k into x of t. The differential equation that we have derived in the last period. Okay, now see here one, in the last period. Otherwise, you open your notebook and see there. Okay, 1 minute. Let us see. See there. This was electrical and this was the mechanical system. And for this mechanical system, we have derived in the last period the equation. In the equation f of m plus fm plus ff plus fk. F of t, it is equals to m into d square xt by dt square plus f into dxt by dt plus k into x of t. K into x of t. So these equations we have derived. These equations we have derived in the last period. In the last period. Now these equations I have written here directly. These equations I have written here directly. Let's say this equation is A. Let's say this equation is A. Okay. Now consider consider electrical network. Okay. Consider electrical network. We will consider the electrical network like this one. This is R. This is L. And this is C. And to these circuits, the voltage is applied. And here the current is I of t. I of t. So from this ones we get V of t, it is equals to R into I of t plus L into dit by dt plus 1 by C plus 1 by C integration of I of t into dt. Okay. Now put I of t. I of t, that is the current. Current is nothing but the rate of change of charge. So that is nothing but the dqt by dt. Rate of change of charge. Rate of change of charge is nothing but the currents. So V of t. So V of t, it is equals to R into I of t is what? dqt by dt plus L d square q of t by dt square, because I of t is nothing but the dqt by dt. So d into d, that is d square, dt by dt, dt into dt, that is dt square, plus this gets integration. Integration of what? dqt by dt. So this becomes q of t divided by c. Q of t divided by c. So v of t, v of t is nothing but equals to L t square q of t by dt square plus r into dq of t divided by dt plus q of t divided by c. Q of t divided by c. So this is our second equation. Let us say the equation number b. Equation number b. Now we have these two equations. We have these two equations. Now see here, equation number A is f of t, it is equals to something, and the equation B is v of t, it is equals to something. Both are the differential equation. Both are differential equation. Equation A and B are differential equation. Compare compare equation A and B. Compare equation A and B. Compare equation A and B. Now see here. If we compare the equation A and B, if we compare the equation A and B, now see here, what is in the A? F of t, it is equals to something. And what is in the equation B? V of t, it is equals to something. So that means force, it is equals to voltage. Force, it is equals to voltage. Compare the equations A and B, we get a force to voltage analogy, because in the equation A there is a force. In the equation A there is a force, that is f of t, and in the equation B there is a voltage, that is v of t. That is v of t. Let us 1 minute. I will highlight that one first, so you will identify this one easily. This is f of t. It is equals to this. Okay, and this is V of t, and this is V of t, this equation. This is V of t. Now see here, compare equation A and equation B. See in the left side. In the left sides, what is there? F of t in the equation A. In the equation A. And in the equation B, what is there? V of t. V of t. So here we will write down mechanical system, and here we will write down electrical. So what is there in the, here is the force that is F of t. Here is the, what is the equivalent terms, that is V of t, that is V of t. Now see here, then there is a displacement, that is x of t. Then there is a displacement, that is x of t, and here there is a charge, that is q of t, that is charge, that is q of t. Here the displacement, that is x of t, and here is the charge, that is q of t. See there, here is d square x of t divided by dt square, and here it is d square q of t divided by dt square. So that means x of t, it is nothing but the q of t. So what is x of t? That is displacement. What is q of t? That is charge. So we can write down the displacement, that is nothing but equals to the charge. That is nothing but equals to the charge. Now see here, there is a speed. There is a speed, that is dxt by dt. So similarly here, voltage, sorry, current. Here is the current, that is dqt by dt. Rate of change of charge, that is nothing but the current. So here force, that is nothing but the voltage, displacement, that is nothing but the charge, the speed, that is nothing but the current, that is nothing but current. So these are the equivalents. These are the equivalents. Now see here, in the equation A, there is a term m into d square xt by dt square. M into d square xt by dt square. And in the V, there is a term L into d square qt by dt square. So that means the mass, that is nothing but the inductance. That is the mass, nothing but the inductance. If we compare these two, then the mass, that is nothing but the inductance in the electrical circuit. Mass, that is M, and here it is inductance L. Inductance L. Now see here, in the f of t, the second term is f into dxt by dt. F into dxt by dt. And in the v of t, what is the second term? That is r, dqt by dt. So that means the frictions or the damper, f, it is nothing but the r. Friction, friction, damper, that is nothing but f, is a resistance, is a resistance R. So we, if there is a dampers, we can directly replace it by resistance, that is R. That is R. And now see here, in the f of t, the third term is k into x of t. K into x of t. Similarly, in v of t, in v of t, in the equation B, the third term is q of t divided by c. So that means the resistance is the, see there. spring, that is nothing but the 1 by C. The spring is nothing but the 1 by C. Spring, spring K, that is nothing but the reciprocal of capacitance, that is 1 by C. That is 1 by C. So that means if there is a spring, so we can replace it by 1 by C, that is the capacitance. If there is a friction, we can replace it by the resistance R. And if there is a mass, then we can replace it by inductance L. If there is a force, we will replace it by voltage. Displacement, we will replace it by charge. And the speed, we will replace it by current, that is dq by dt. That is dq by dt. So this is your force to voltage current, force to voltage analogy. Force to voltage analogy. See there, this one. And these are the equivalents. And these are the equivalents. Force to voltage analogy. In force to voltage analogy, first we will draw the mechanicals and then we will draw its electrical equivalent. Electrical equivalents, or vice versa. Electrical is given, then we can convert it into mechanical also. If the voltage is there, then we will say it is a force. If there is a charge, then we will say it is a displacement. Or speed is there, then we will say it is a current. If the mass is there, then we have the inductance. And friction is there, then we say it is a resistance. And the spring is there, then we say it is a reciprocal of the capacitance. Reciprocal of the capacitance. So this is your force to voltage analogy. Force to voltage analogy. Hello, hello students. Understood
Yes,
this
sir.
one? Hello, hello.
Yes, sir.
Yeah, yeah. If you see the previous exam papers, you will find out there is always a one questions of at least 5 marks on the this one, uh, physical systems. Sometimes they ask to write down the differential equation. Sometimes they ask to draw the force to voltage or force to current analogy circuits. Now see here. Here we will see uh, force to current analogy, F2I analogy. F2I analogy. Now see here, for this one, for this one, now we will consider the circuits that today that we have studied. That is I. Here is the I of t. Here is the I of t. Then we have that is R, L, and C. And C. So just now that we have derived the equation. Just now that we have derived the equation. Now see, what was the differential equation in terms of I of t? See there, in terms of I of t, this equation that we have derived, I of t, it is equals to what? I of t, it is equals to what? C into d square phi of t divided by dt square plus 1 by r d phi t by dt plus d phi t by L. D phi t by L. Now, this we will write down here. This we will write down here. Now, for this one, for this one, I of t. Oh, sorry. I of t, it is equals to I of t, it is equals to what was that one? Uh, क्या था? C 1 by R 1 by L. C D square C D square phi t by dt square plus 1 by R d phi t by dt plus phi t phi t by L. So this is our differential equation. Let us say this equation is C. This equation is C. Now see, the equation A is a mechanical equation. Equation B is a voltage equation in electrical circuits, and equation C is a current equations for electrical circuits. Now compare equation A and C. Equation A and C. Then we get F2I analogy. Then we get F2I analogy. Here mechanical circuit, and here we have electrical circuits. Now see here in the mechanical circuits, okay, in the equation A to the left sides there is a force, and in the electrical circuit, see in the equation number C, I will highlight this one. This is equation C. This is equation C. In the equation A, left side there is a force, and in the equation C, left side there is a current. So we can write down here force F of t, that is current I of t, that is input. Input is the force and input is the current in case of electrical. In case of electrical. Now then see, there is a displacement, that is x of t, and here is the flux, that is phi of t. Here displacement x of t, and here the flux. Here we have the flux, that is phi of t. Then there is a speed, that is dxt by dt. Here there is a voltage, that is rate of change of flux. If we take the rate of change of flux, here we have taken the rate of change of the displacement. So here we will take the rate of change of flux. Here is x of t, here is dxt by dt, here is phi of t, here is the d phi t by dt. D phi t by dt is called as voltage. Is called as voltage. Now see here in the equation A, there is a m. To the see the right side, there is a m, and here in the equation C, the first term is C. So here is the mass. Here is the mass. Mass, that is m, and here is the capacitance, that is C. That is C. Now see there in the right side. See there in the right sides in the equation A, there is F into dxt by dt. So that means there is a damper or the friction, that is F. See the second term in the equation number C, that is 1 by R. So here is the friction or damper, that is F. Here is reciprocal of resistance, that is 1 by R. See there. Here in the f of t there is f into dxt by dt, that is the second term. Similarly in the equation C, there is 1 by r d phi t by dt. So that means F is nothing but R. F is what? Friction. Friction or damper. It is not a force. It is a friction or the damper. So reciprocal of resistance, that is 1 by R. And see here in the equation A, the third term is K into X of t. K is nothing but the spring. So we will write down here spring. So we will write down here spring, that is K, and here in the equation C the last term is phi of t divided by L, so that means it is reciprocal of inductance. Reciprocal of inductance, that is 1 by 1 by L, 1 by L. So this is the force to current analogy. Force to current analogy. Okay. Now see here, we can summarize this in a one sheet like this one. Okay. Here we will write down the summary. Summary. Here we will write down mechanical here voltage analogy, and here we will write down current analogy. Current analogy. Here first is force, that is F of t. Here voltage V of t, and here it is current I of t. Okay. Then here the displacement, that is x of t. Okay. Here the charge q of t, and here the flux phi of t. Flux phi of t. This is the flux. Flux phi of t. Then here is the speed, dxt by dt. Here is the current, dqt by dt, and here voltage d phi t by dt. D phi t by dt. Here the mass, that is m. Okay. And then mass is inductance L, and capacitance. Are you all able to understand this? Mass is perfectly understood. Initiation phase we have done, and then stakeholders. Inductance L. capacitance C. Then the friction or damper, that is F. Here, what is the friction damper? That is resistance in F to V. In F to V analogy, that is resistance, and here it is reciprocal of resistance. Here it is resistance, that is R, and reciprocal of resistance, that is 1 by R. And then the spring K. Here in F to V analogy, spring is nothing but the reciprocal of capacitance and the reciprocal of inductance. Here it is reciprocal of inductance, that is 1 by L, and reciprocal of capacitance, that is 1 by C. That is 1 by C. So this is the simple table. This is the simple table. This is F to V analogy. This is, we can say, this is F to V analogy, and this is F to I analogy. This is the table. This is the table. In case of mechanical system, if there is a force, in F to V analogy that we have voltage, and F to I analogy we have current. Displacements in mechanical, it is become charge in case of F to V, and it is flux in case of F to I. The speed in case of mechanical, there is a current in case of F to V, and the voltage in case of F to I. Then there is a mass in F to V, there is a inductance, and in F to I it is replaced by capacitance. Friction of the damper, that is F in mechanical, it is replaced by R in case of voltage analogy, and it is replaced by reciprocal of 1 by R in case of current analogy. And the spring in case of mechanicals will be the
Sir,
equivalent of,
1/3
hello, it is
रेसिप्रोकल
a
ऑफ कॅपॅसिटन्स येणार ना
कशाचा
व्होल्टेज अॅनालॉजी मध्ये
reciprocal of
कॅपॅसिटन्स येणार ना
RLC. Here is the capacitance. Sorry. Here is the capacitance. Uh, Here is the capacitance. झालं झालं नाही नाही this is L. LRC ना. This is LR 1 by C. Okay. It's okay na now. And in case of there is a spring in the mechanical, then here we have
वन
reciprocal of capacitance, that is 1 by C in case of force to current analogy. Force to current analogy. C. No. Something is wrong. C 1 by R, and here
तर
is 1
दोन्ही
by
पण
L.
उलटी झालंय.
उलटे झाले होते. This is 1 by L. This is 1 by L. हा टेबल नेहमी करता लक्षात ठेवा. This table you have to remember always. Okay, this is important. This is important because if we remember these tables, then we can convert mechanicals to electrical either in voltage or either in currents, any one of them, any one of them. And tomorrow that we will see the numericals based on this one. Okay. So now today we will stop here. Today we will stop here. Don't
सर
leave
तुमचं
right now.
उद्या लेक्चर
Yeah.
असणार
हॅलो. नाही उद्या नसेल, परवा असेल आता.
सर परवा
उद्या
एक्झाम आहे
अच्छा परवा एक्झाम आहे का? मग बघूया त्यांनी काही मॅनेज केलाय का किंवा कसं आहे तर माहिती नाही मला. मी विचारेल त्यांना, मग बघूया त्याप्रमाणे लेक्चर्स होतील तुमचे. ओके. लेट मी डाउनलोड द अटेंडन्स.